Hi, this is Nick LaRue, and this is my presentation on the longest common substring in linear time. So the problem is the longest common substring problem, of course. So what does that mean? So substring can be defined as a continuous sequence of characters in a string. So in other words, if you look at the examples above, if we have a string such as A, B, C, D, E, DE would be an example of a substring. And you could also have CD as well. But the second example, A, B, C, D, E, B, E could not be because they're not contiguous, because they're not right next to each other. That would be considered a subsequence. So we're looking for a substring in this situation. So the input we're given in this problem is two strings. We'll just call them S0 and S1. And basically on the output, the longest string, which we will call S2, which is a substring of both S0 and S1, a shared substring. So basically the naive solution is we're basically going to go one by one through all the substrings of the first string and every substring in the second string and compare them together and just keep track of the maximum length substring. The problem with the solution is that it takes n to the second time, which is not really the solution we want. We want a solution that's going to get us the longest common substring in linear time. So how do we do this? So the way we can do this is actually through a structure called a suffix tree. So this is going to allow us to solve this problem in linear time. And a suffix tree, as you can see to the right, has no more than n leaves. So if we're given a set of strings, the amount of leaves it has is going to be no longer than the length of the string that we're given. Every internal node besides the root has at least two children, and each edge contains a subset of a set S. And if we follow the path of the tree is going to give us a different suffix of the given set. So for this particular problem, we're going to want to build something called a generalized suffix tree. So the difference is that a generalized suffix tree is going to allow us to build a suffix tree of multiple sets. For example, if we're given that input, the S0 and S1, we're going to want to be able to put them both into a tree and then compare to see which one has the longest path. That will give us our answer. So the way we do this is we actually have to keep track of which suffixes belong to which set. And we can do that by basically attaching different symbols. In this example, $0 and $1, as you can see to the right, gives us different examples, different references to where each suffix belongs to, as well as the starting and end position of the characters themselves. And the longest common substring, the longest path down to a node, which is from a suffix that comes from both S0 and S1 for this particular problem. So the algorithm that I'll be presenting on today is called McCreight's algorithm. McCreight's algorithm allows us to build a suffix tree in linear time for both space and time complexity. And it builds a trie of all suffixes of the given strings. And one of the things that makes this algorithm special is it utilizes an auxiliary data structure that are called suffix links, which we'll describe in more detail later. So basically, a few ground rules of McCreight's algorithm is that there's an S1 rule in the paper basically states that the final character of S may not appear elsewhere in S. But in the case that a string does not satisfy this, it can be extended by padding up the new characters. So if we have, for example, ABAB, we can append the character C to it to make it so it doesn't break this S1 rule. And the strings represented by sibling arcs of T must begin with different characters as well. So to keep that in mind moving forward. So some terminology that we have to understand from McCreight's algorithm is that McCreight refers to things called a locus, which is basically the node at the end of the partial path named by the string. An extension of a string, U is any string of which U is a prefix. And extended locus of the string U is the locus, the shortest extension of U, whose locus of the short set extension of U, whose locus is defined. And the contracted locus of the string U is the locus of the longest prefix of U, whose locus is defined. These will be important later on when we're going through the actual algorithm itself. So because we're going to use this to build a generalized suffix tree, we're going to have to make sure that we're keeping track of the different symbols, like we were talking about before, $0, $1, to be able to differentiate the different string sets. And then we'll also have to keep track of the starting and ending position of each suffix in our given sets. So to start out from McCreight's algorithm, if we're given, for example, a set of A, B, A, B, again, in this case, we're appending C because of our S1 rule. What's going to happen is we're going to start out with an empty tree. And then we're going to go through every suffix starting from the very beginning of our set, and then go to the very end and build a suffix tree from left to right. So as you can see, we have an empty tree, and then we go on, and it starts with the longest suffix, which is at SUF1. And so we create a new node out of the root, basically out of the entire string itself. And then we move on, and then we go to the next part of the string, which is BABC, which is SUF2, and then we create a new node out of that. So now that we've created those two nodes, we go to SUF3. And what we're going to do is insert, now this is the ABC, into the tree. So what's going to happen is we're going to insert SUF3 into the tree, into the extended locus of head. We're going to basically create a new terminal node and split the incoming arc, the incoming node. And if necessary, we're going to insert tail constructed from the new terminal node. So what that means is when we previously, for example, have ABC, we're going to look at our ABC, and we're going to see that beginning, the prefix matches ABAC. And we're going to go down this path, and we're going to take the head of ABC, which is AB, and then we're going to use that to create the new non-terminal node. And then we're going to use the remainder to create a new terminal node down here called ABC. And the tail of ABC as a new node we call C. So, what do I mean by head and tail? Head basically is defined as the prefix of the suffix I. So, and tail is considered to be the suffix. So in this case, we have ABC, and AB would be head, and C would be the tail. So if you see here, we're going down to suffix 4, where we have BC. So BC is basically going to go down, and it's going to look at this. It shares a prefix of BA, BC here, and we're going to split that node up into ABC and C. So what's going to happen is going to create a new terminal node of B. It's going to create a new node with the remainder of ABC, and then with the tail, create a new node called C here. And then after that, which is, we don't see the step here, but it's going to go to the very end of the string C. It's going to see that there doesn't exist a starting character of C yet, and according to McCreight's algorithm, we cannot. We have to make sure that each node starts with a different character. So as a result, we're going to create a new one called C here. And just to make it more clear, here's the head of the suffix 1 and the tail, and then the head of suffix 2, and then the head of suffix 3. So how can we find the extended locus of head in a way to get this to linear time? So basically there's a lemma that basically says if head I-1 can be written as we'll call it XO for some character X and some possibly empty string O, then O is a prefix of head sub I. So we're going to prove this by induction on I. So if we suppose head sub I-1 equals XO, this means that there's some J, a J that's less than I, such that XO is both a prefix of both suffix sub I-1 and suffix J-1. Thus, XO is a prefix of both suffix J and of suffix I. Therefore, the definition of head, XO is a prefix of head, and O is a prefix of head sub I. What this means is that a prefix of head already exists somewhere in the tree. As a result, we can create pointers or suffix links to that node and jump to it. And from each terminal node, when the locus of XO, which is the locus of XO, where X is a character and O is a string, a suffix link is introduced pointing to the locus of O. So the first step in this algorithm is essentially we're going to identify a string we're going to call XUW. So head sub I-1, in other words, the previous head is going to equal this XUW. And because it's the previous head, we know it's going to be a prefix of the incoming suffix. Okay, so we have XU is defined as the contracted locus of head, and X is a string of at most one character, which is empty, only if head sub I plus 1 is empty. So if we see here, what we're going to do is we're going to find XU here, and then we're going to create a suffix link to the prefix here, which is U, which we're going to label as C. What it's going to enable us to do is actually jump to this node here and start doing the next step, which is called rescanning. And so, we know by the definition of head that XU already exists in the tree. We're going to rescan W by first going to node F. And so if W is larger than P, then a recursive rescan begins from F. And if P is the same size or shorter, then we're going to consider it to be complete. So in this case, it ends up being larger, so we continue to scan, and we come to a new node called D, or not a new node, but an existing node called D, which is now the locus of UW, and we move on to the next step. So here, if it doesn't already exist one, we're going to create a new suffix link for XUW to point to D. So now we have a suffix link that points from D to W. And then we proceed to search deeper for the extended locus of UXY. So now from D, we're essentially going to keep searching down one by one, left to right, until we find Y and we fall out of the tree. So in this case, we find it here, and we go in here, and then we find out, and we go back to W, and then we create a new tail I. And that's the end of our algorithm. So essentially what we're going to do is we're going to keep on repeating this process over and over until we fully built out our generalized suffix tree. So now we have our generalized suffix tree constructed. We can start at the bottom of the tree and search for the node that is shared by both string sets. And then we have our longest common substring. And And that's our presentation. Thanks for listening.